So what I wanted to do is kind of talk about some of the different applications I've seen personally by observing the market in upstream oil and gas from a geoscience perspective. I got 3 examples up here that I've seen, and I have a couple more in my head that I've seen that I didn't make any slides for because just because of time constraints. But one of the ones that I think would hit most to home for geoscientists is the use and application of well logs, and how messy well log data can be, depending on where you get it and how it's been processed. And so here's an example showing logs with multiple runs from different tools and gaps in the data. Very common thing, we all have to deal with this. It's a reality that we live with as geoscientists, or some of us focus a little bit more on the petrophysics side. You live it a lot more than I would. But in this example, I'm showing you a data set that has these gaps, and on the right, I'm showing you kind of the goal. The goal would be, what if I can predict the responses between areas where data is missing? How would you do something like that? The question is a function of data cleanliness and the amount of data you have and how relevant it is. And when you can answer those questions confidently, you can actually infill logs of this nature. So here's one example, right? You have a caliper, you have density log, you have gamma ray, neutron source, a variety of different tools, and sonic tool as well, with a lot of missing data sets on them. And all those missing data sets, let's say if you had, in this case, in the Permian, 200,000 wells or 300,000 wells or something like that, that would constitute a pretty large data set. So this is very different from a lot of other techniques where people would look at offset wells and try to guess, based on 5, 6, 7 wells, what's going on in these different zones and try to kind of splice that together. What you're looking at is if you have a large enough data set and you've captured all the variance in that data, you're capturing all the different scenarios that are possible in a given area. So if we just focused on the Permian and we had 200,000 wells, you can actually build some models that will take the interaction between all those different logs and the sheer volume of data you have, where you have data in those depths, or you don't have data in those depths, where you have certain tools missing and other tools not missing. You can actually infill. And so what we're showing here in the red is 0 and 1. And so if you go back and forth, you can see that the real data is here, and the synthetic data, which we're infilling, shows up as 1. So 0 to 1. 0 means it's real data. 1 means it's synthetic. So this was all done using some of the more modern techniques in the machine learning space, having a very large data set available to you that has been standardized and cleaned, like Dr. Jones said, 85 to 90% of the work. And then you can start applying some of the latest algorithms. And new algorithms are coming out all the time. Another application that you're going to see a lot of, and how many of us have sat over in our workstations picking tops over a variety of logs so we can build our horizons out for all kinds of different reasons. If you're working on volumetrics type problems, if you're trying to train or provide an input for seismic processing, things of that nature, you would kind of want to know where these interfaces occur. Let's say you have 2,000 wells, and you said, man, after 400 wells, you picked your different horizons. You say, I'm really tired. And maybe 400 wells is enough in this case. You built your training set. So you've trained on 400 wells, all the different log picks. And then based on the learnings these algorithms have had by watching you and observing you do this, you can apply it on the other 1,600 wells in that case. And so big data is all about finding that kind of lever. At what point have you trained the algorithm enough that can really augment you and make you a better geoscientist or petrophysicist? So this is something that I've seen a lot more of, and you'll see a lot. So on the left, you have expected. So these are the actual tops that were delineated by somebody training the data. And on the right is after they've trained it, applying it to a different data set where it wasn't trained, getting that top predicted, and then going back and double checking it with somebody, going and doing it manually, right? So if you've done your job, you've done a good job training the data set, validating it, these will be very similar. So the idea is, well, we don't have to sit there and dredge over 2,000 wells of picking. Maybe you only need 800 of them or 600. At some point, it will be cost efficient and time efficient for you to employ some of these algorithms to augment you and make you a better geoscientist. Excuse me. I don't know how many of you had an opportunity to see the cover of the December bulletin for the Houston Geological Society, but that's this picture right here. And this is kind of interesting. So this is a seismic volume prior to migration, so very early on in the process. So the data quality is pretty bad. It's a little rough, and the first thing you want to do is kind of pick the top of a salt domes or salt bodies. And after you've done that, then you run through migration process and get a little bit of a better picture quality, and then you might work on the bottoms and actually identifying the bodies themselves. And so what you're seeing here is the human interpretation and the subsequent machine learning interpretation when you've trained at this point in the data. And I don't know about you guys, but when I look at this, can you tell which one is the machine versus which one is the human? I mean, they look virtually identical, right? So the top one was done by individuals, by people sitting over a desk and classifying these manually, versus this algorithm here on the bottom that did that in a more automated fashion. So what happened is somebody worked on the data set, identifying them, and then we applied that learning to a completely different data set and basically took that augmented version of the interpreter and applied it in areas where no one had interpreted before, and then we went back and did it manually to see what the difference would be without showing, right? And it was very, very close. So imagine a world where you've captured a lot of these learnings and you're able to apply this in between each iteration from a seismic perspective, right? A significant amount of time and money is lost at that bottleneck just waiting for someone to turn to the data for the next processing step. So at each one of these steps is an opportunity to cut a significant amount of time so that the computers that are waiting idly for this kind of processing power, which are quite expensive, aren't waiting anymore. So I think that's a really interesting application there. And you would then follow it up with every other step in the processing standpoint of, well, I pick tops here, I pick bottoms here, I pick bodies here, and before you know it, you've really cut a lot of time and effort out of each step in the processing workflows. And with that, I wanted to introduce Andrew Silver, who was also in the program with me. We both graduated this past May, to give kind of a glimpse of what he worked on throughout the program.
All right. I have a few slides here. They were just 3 slides out of over 40, and it'll be a little sampling. Some of it is intellectual property of my company, and so you'll see some parameters blurred out because I couldn't show everything. But a quick little comment. The theme of the night is about AI. I wanted to point out that things like this, these aren't just AI, these are also IA. These aren't just artificial intelligence, these are also intelligence augmentation, making humans better by leveraging the strength of inexpensive compute from computers. So there's a lot of fear that gets tied up in the issue of AI, but it's also important, I think, to reframe things in terms of intelligence augmentation. We can use these tools to make our lives easier, right? So with that in mind, I did a project where I had to build an explanatory model. So not just a predictive model, but a model that would predict, and then I could then use to explain what was happening inside of the physical processes of a system. And for this purpose, I built a predictive model, and as Dr. Jones mentioned, there are target variables. It is often important for the target variable to have a somewhat symmetric distribution. Maybe not perfectly normal, but you still want it to tend towards symmetric. So there's a thing called Tukey's ladder of powers. And some of you may have heard of log transformations before. You can also do square root transformations. It turns out you can do any kind of transformation you want as long as it gives you a nice symmetric distribution, and then you can transform things back afterward. But if you're going to use a central tendency, the middle of something, to make a prediction, you want that to be somewhat balanced, because otherwise outliers on one side or the other side will start skewing your result and predictions off. So if you want it to be stable, you want it to be balanced. That's one thing to keep in mind. Also, there's a lot of tools along the way that you can use as you're exploring your data. A very commonly used one is principal component analysis. You can do this with linear correlations or with quadratic correlations, which have curvature. Most people just do linear. And these are good for exploring high dimension data. So in this case, I'm showing 11 dimensions, and from that, I'm also generating 11 principal components. So everyone here, I presume, has heard of strike and dip before, right? You get a lobe of sediment on an inclined plane. It's going to tend to go down because of gravity, right? And it's going to tend to be elongate either along strike or along dip. And strike and dip are perpendicular to each other. So these are two principal components that we work with all the time and we're very familiar with. Now take that concept into any other type of variable. That's essentially what principal components are. And each principal component is perpendicular to all the others. Even if it's in 11-dimensional or 16-dimensional or 200-dimensional space, each one's going to be perpendicular to all the others. And from this you can come in and start seeing that certain variables tend to run with each other. Certain variables tend to have effects in the same direction or in opposite directions, positively or negatively correlated with each other. So this is a very useful tool. And sometimes you can use it when you have too many variables to just decide, I'm going to use a principal component instead of these 7 variables, because I can't have all 7 variables in my model, it would destabilize it. But I can take the principal component extracted from those several variables and have a stable model that way. So this becomes a useful tool sometimes, both for exploring your data and for stabilizing models. Dr. Jones also talked earlier about cluster analysis. I found a very useful application of cluster analysis, in this case hierarchical cluster analysis. I'm also a fan of k-means. Some of you may have toyed around with self-organizing maps. I understand some seismic software likes to use those. I chose HCA for a problem because it seemed to give me more intuitive answers which were more easily explainable. But I had a problem, and that problem was autocorrelation. Spatial data and time series data often has an issue of autocorrelation. So what is this? So a crude example would be, say I have a radio and I have my favorite station and I want to listen to my favorite songs. I take that radio and I put it next to a big huge power generator which is humming away at a really loud volume. I can't hear my songs if it's next to that big source of noise. Autocorrelation is kind of like a big generator pumping out tons of noise. If you have your other data close to that, it's really hard to hear the signal coming at them because it's getting overshadowed by all that autocorrelation. So I had a lot of autocorrelation in the spatial data, and most of the data in the real world has some spatial component and often some time component too, and I needed to handle that somehow. Well, first off, I started looking at field names, but man, there's one field, the Eagleville field, that covers most of the Eagleford play, right? And then there's a whole bunch of other fields which are really small. And some of these were very significant, but overall it just wasn't working. So I had to make my own field names. So I took a number of geologically oriented variables, which I've kind of blurred out here. Again, intellectual property, apologize for that, but I used them to build my own fields. And then I used these fields to help explain the spatial variation of the Eagleford. And in quantifying that variance, I was able to build a more stable model which didn't have the same issues of autocorrelation that I might have had otherwise. And then I built a linear regression model. Because my end goal was having an explanatory model. My objective was not merely to predict, my objective was to explain. And with the linear regression, we get parameter estimates. And I can combine these parameter estimates together and predict the production coming from a certain sequence of events. If I have a certain choke size in a certain area with a certain oil in place and other variables, so forth, I can get a fairly good prediction of what production I'd likely get. And then I can start making predictions about how would my production be affected if I change that variable up or down. And then if I know the cost from a vendor of what a certain piece of equipment will cost me, I can start making economic decisions based on this. Should I have a rotary steerable or not? Should I use a bigger choke size or a smaller choke size? I can start turning knobs to improve production. And in a downturn like we've been suffering through for the last few years, this can become very important for maintaining the survivability of a company, right? And also I mentioned earlier the t-test. You'll see it manifest here as t-ratios. I just wanted to tie back to those Guinness. And so, yeah, that t-statistic, it's still used profusely throughout statistics. So thank goodness people were fans of beer and it led to some innovation a long time ago. But interpreting these and stabilizing models is a non-trivial task. And there is a lot of art involved. And because I think we're doing good on time? Yes? Quick little comment about these things. I was chatting with a gal, and she was saying that a lot of machine learning tools are kind of like a car. You build the car and then you can drive it. I said, okay, I won't argue with that necessarily, but I propose a metaphor of tools. These are statistical tools. Now, if I was to get a PhD statistician, he could figure out how to make a new tool. Great. But he might be able to figure out how to make a new car too. Right? This is metaphorically speaking. But I like the idea of tools more than automobiles, because with a tool I can go into a workshop and I can craft a solution. Right? When I was working on my capstone at A&M and I came up with this approach for handling autocorrelation, it was not handed to me on a platter. No professor told me try this. I took the tools I'd been taught and I applied them until I found a solution. I had to go into the workshop and craft a solution, building it piece by piece. So getting back to the analogy of tools, think of a rotary saw or something. You don't necessarily have to know how to smelt the iron or mill the carbide bits, but you do need to know how to use it so that you don't cut off your fingers, right? So there are a lot of machine learning tools out there. Please don't use them unless you know the pitfalls. You can cause a lot of damage by encouraging the wrong types of investments by misapplying these tools. I'm not saying you need a PhD in statistics. You don't need to necessarily make new tools, but you do need to know the pitfalls of the tools you're using. Right? So you can use these like a workshop, crafting your own solutions, as long as you make sure that you have valid solutions along the way. So, and that's what I have, and I guess I'll be passing it on, and unless anybody has questions.
Could you talk a little more about your transformations, the log transformation, the cubic? I've never seen the cubic used before.
Mhm.
And is there a property that's associated with that makes it better? You had it
Yeah.
captured in your slide.
Yes, the property which makes it valuable is that it's more symmetric. I mean, just look at that. The outliers being displayed as being beyond
They're on both
1.5 of
sides.
the interquartile range.
Yeah.
The outliers are fairly balanced here, right? So they're not pulling the central tendency in one way or the other. And that's why I did that. And at the end of the day, there's a way to undo that when I'm making my final interpretation. Yeah?
Yeah, so you sometimes can you do it when your data's not symmetrical, like log normal or something like that, where it's
Oh yeah, that's the whole point.
consistently that way?
Like, so here you have barrel oil equivalent, and that is definitely not very symmetrical. It's very skewed, right? So the mean is not near the mode at all. Got a lot of outliers on one side. But running through these transformations, you can often find one which will give you a nice balance.
So that's what you gotta look for?
It's wise to do it, yeah, if you want to have a more valid interpretation. Because otherwise the outliers will pull your interpretations to the side and destabilize models.
There's a lot of log normal data out
Yeah,
there.
Mhm.
a lot.
A lot.
Yeah.
And this is one of the ways you handle
Amazing how
it.
that-
And there's other trick. This is for the target variable. It's especially important for the variable that you're trying to predict. For variables that you're using to make that prediction, sometimes things like central limit theorems make it so that you don't necessarily have to transform every single variable, but it depends on the use case. Right? Did I see another question? Are we good to move on?